Thank you for the warm introduction. Yeah, it's a great pleasure for me to be here. And let me say, it's a great honor for me to serve on this Abel Selection Committee. And I got to see the achievement of many great mathematicians. It's a humble experience for me. So today, I will talk about a little bit about my own research. Okay. So my own research, the topic I choose is a little bit special. It's called Conformal Geometry on dimension 4, on 4 manifolds. So let me begin by saying a little bit, explain a little bit about the title and the subject. So on a manifold, for example, on a sphere, and we have a metric, G, a distance function. And conformal means on a metric G, we change the metric to another metric called G hat. So G hat is conformal to G means the angle preserving. That means for each two vector in G hat, the angle between two vectors is preserved. Okay? So that's what we call conformal. And so for that reason, we denote G hat by G hat equal to a positive function rho times G. So the length of a vector is stretched, but angle is preserving. That's called conformal. And for this talk, to emphasize rho is a positive function, I will usually denote rho to be exponential 2w. So in my notation, GW is in the same conformal class as G, and is exponential 2w times G. And in geometric analysis, what we usually do is using methods in analysis, and frequently it's methods in partial differential equations, and spectrum analysis, functional analysis, and to study problems in geometry. And the frequent subject to say that is to express it in terms of sign of curvature, or size of a curvature, or sometimes you will see in this talk the sign of the integral of some curvature polynomial. Okay. And in conformal geometry, we study these curvature changes under conformal change, and we study conformal invariants that are quantity which is preserved under conformal change of metric. And some of them are pointwise quantity, and some of them are integral quantity. And in this talk, we will put emphasis on a sign of a special integral quantity, as we will see. So the outline of my talk is the following. First, I will say a little bit about what happens on 2 dimensions. Okay. So in that case, there is the Gaussian curvature, and then there is also another curvature called scalar curvature, and that's related to second-order partial differential equation. And then I quickly move to conformal invariants on 4 manifolds. And in that case, it turns out instead of relating the curvature to a second-order PDE, we will relate them to a 4th-order PDE. 4th is because it's on 4 manifolds. And then we study conformal invariants on compact 4 manifolds. And I talk a little bit about how about on closed 4 manifold, that's manifold without boundary, and on 4 manifold with 3-dimensional boundary. And then we relate the study of conformal geometry to a little bit of mathematical physics, string theory, and there these invariants are related to a concept called renormalized volume. Volume is infinite, but you renormalize it, okay? Renormalized volume. And then I talk a little bit about the recent development of compactness results on conformal compact Einstein manifold. So I will explain what does that mean later. So let me start by keep a quick review of what happened on compact surfaces. Okay. On compact surface, think about sphere, two spheres. And the Gaussian curvature is the quantity, and which the most important formula is something called Gauss-Bonnet formula. So it's pi Euler characteristic is equal to integration of Gaussian curvature, something we all learned in college. Okay. So this, the left-hand side, Euler characteristic count the number of genus of the surface is a topological quantity. And the right-hand side, Gaussian curvature and integration of Gaussian curvature is analytic and geometric quantity. So this formula is a wonderful formula which tells you the relation between topology, the shape of the manifold, to some analytic quantity. And one theorem, the most famous theorem, comes from Gauss-Bonnet formula, is called uniformization theorem. That is, you can actually classify two surfaces according to not only the Gaussian curvature, but the sign of the integration of the Gaussian curvature. So that means the Euler characteristic already classified the two surfaces. So what does that mean? That means if you look at the sign of the integration of the Gaussian curvature, that's pi Euler characteristic, and then it can have a positive sign, 0, or negative sign. And according to the sign, we know when then in the conformal class, you can deform the curvature to be identical 1, 0, or -1, and you classify it according to isometric, to the hyperbolic surface, to the flat surface, or to the two sphere. Okay? And that's called uniformization theory. So that's a dream theorem everybody is trying to do to see how to generalize results of this type to high-dimensional manifolds. And there is spectacular success on 3 manifolds. Today, I will report a little bit about what happened on 4 manifolds, a slice of it. So, let's see the basic tool we use, analytic tool. To solve the Gaussian curvature equal to identity, a constant, and there is this second-order PDE, Laplace of W, and plus Gaussian curvature. And then under conformal change is Gaussian curvature exponential 2W. So it's a second-order PDE, but with a semi-linear term, exponential 2W, nonlinear term on the right-hand side. So it's a second-order nonlinear PDE. And the way to solve the Gaussian curvature is through the variational method, and there is a famous formula called Moser's functional, and that's the functional of the energy gradient W plus 2 times Gaussian curvature times mean curvature, and then subtract a normalization of the quantity. And that's introduced by Jürgen Moser, and to study this functional. And it turns out this functional also has another geometric meaning, okay? And that's related to Ray-Singer and so-called Polyakov formula. It turns out this functional also expresses the determinant of the Laplace of GW vice the background metric G. Okay? It's the quotient of this log determinant, and this log determinant is defined via a regularization process of zeta functional, and that's introduced by Ray Singer. And there are lots of work in this subject. I will not mention details. Okay, and then a partial attempt to generalize this two-dimensional work to high dimension is to study other second-order elliptic operator. And one attempt is to study the conformal Laplace operator, L. L is equal to minus Laplace, like this in two dimensions. Remember, we studied the Laplace operator. Here we study Laplace, but plus a potential function, and that potential function turns out to be the scalar curvature of the metric. I will say a little bit about scalar curvature later. And this operator also has conformal covariant property. And that is, if we change the metric G to G hat, a conformal change, this operator prescribes the scalar curvature R hat of G hat in this semi-linear PDE. LG on U is equal to R hat times U to a certain power. And this equation has been extensively studied in 1980 to about 2000 by a series of workers, and that's called the famous Yamabe problem. And it turns out when n is not equal to 2, the variational functional to study this equation is quite simple, and that's just the integration of the scalar curvature, Rg hat dvg hat. You vary g hat in a conformal class, the critical metric of this functional Euler-Lagrange equation gives you R hat equal to constant. And for that, the sign played by Gaussian curvature is replaced by an invariant quantity called Yamabe invariant. And Yamabe invariant is just this integration and normalized volume, and you take inf of thing in a conformal class. So this is an invariant only depending on the conformal class of the metric. Okay, and that is an extensive study of the Yamabe problem. And now in my talk, I will introduce something on four manifold. So it turns out that on manifold of dimension greater than 2, there are many curvature notations. And that includes Weyl curvature, Ricci curvature, and scalar curvature. Okay. So scalar curvature is an average of Ricci curvature. But besides this, Ricci curvature is a measurement of the volume of the manifold. But besides this notion, there is also the notion called Weyl curvature. So let's look at the Gauss-Bonnet Chern formula on four manifold. So this is, turns out to have two terms. One is the Weyl term square. The other is a combination of the scalar curvature square minus Ricci square. Okay. The problem will become delicate because we have a minus sign here. So there is some cancellation behavior happening. Okay, so then the Euler characteristic is still the chi-m is still the Euler characteristic, but what does Weyl curvature does? Weyl curvature measures the obstruction to being conformally flat. So what does that mean? That means when the Weyl curvature is equal to 0, identically equal to 0, like in Euclidean case, then it means in a neighborhood of the point, it is conformal to a flat metric. So it measures how flat the manifold is. So for example, the sphere and the Euclidean space Rn all have Weyl vanishes. But in this formula, one thing we want to emphasize is the conformal invariant property. And that's expressed in the following expression. It turns out Weyl curvature under conformal change has pointwise invariant property. It just pulls out the conformal factor. And the effect of that to us in full manifold is if you have d volume of GW, it turns out to be exponential 4W d volume of G, and that exponential 4W cancels out with the weight of exponential minus 2W. So this volume form, Weyl square d volume, is a pointwise conformal invariant. So as a consequence, the integral is a conformal invariant. Okay. And so we have this formula. On the left-hand side is a topological quantity, so it's invariant under conformal change. On the left-hand side, on the right-hand side, there are two terms. One is an integral, in fact, pointwise conformal invariant, and the integral conformal invariant. Our conclusion is this second expression on the right-hand side is also an integral conformal invariant. And so for that reason, we denote the second term by sigma 2. I will explain the notation later. So the consequence is the second term in the Gauss-Bonnet formula is an integral conformal invariant. Now let me justify a using of the symbol sigma 2. Okay. So it turns out that there is another way to view at Gauss-Bonnet formula, and that's using Cardan's notation. Cardan introduced this formula, something called the Schouten tensor. So Schouten tensor turns out to be a combination of Ricci to scalar, so it's a tensor. And in terms of this tensor, the full curvature, so it's a full tensor, is a direct decomposition of Weyl with Schouten. And we already know that Weyl curvature is a pointwise conformal invariant. So that means to study the full curvature tensor, how does that vary under conformal change? All the effect is on the Schouten tensor. So we should study Schouten tensor under conformal change. So for that reason, we begin to look at the Schouten tensor, and the sigma 1 of that, sigma 1 though denote trace of the Schouten tensor turns out to be scalar curvature. And so scalar curvature, that's the study of Yamabe problem. And so on full manifold, it is therefore natural to study the second symmetric function. Second symmetric function of a metric is sum of lambda I, lambda j, okay? Summation of the eigenvalue, and is 1/2 of the trace square minus the norm square. So if we do the computation in full manifold, sigma 2 of the Schouten tensor is this Gauss-Bonnet integral. It's a quadratic curvature. And when k equal to n, if we take sigma 4, say on full manifold, the sigma n of Ag is the determinant of the metric. And that's the study of the typical nonlinear PDE, the Monge-Ampere equation. So this suggests that we should use techniques in study Monge-Ampere equation, this fully nonlinear PDE, coupled with the study of the second order PDE to study something in between sigma 2 on full manifolds. So let me say a little bit of how it's going about. Say, for example, uniformization suggests we should study classify manifold according to some model example of when the curvature is a constant. Sigma 2 is a constant. So let's do it under conformal change. So under conformal change, this Schouten tensor under conformal change turns out the leading order term is hashing the second mixed derivative of W plus some first order combination. So using that, one can see sigma 2 of AGW is this term. The leading order term turns out to be Laplace square minus hashing square, and plus some second order, first order combination. So we are going to study the PDE under conformal change. When is this equal to constant? Looks complicated, but on the other hand, in the literature, we already have lots of tools to study sigma 2 of hashing of a U. Okay? And the leading order term is Laplace U square minus hashing U square. So we build on a technique. We know how to study hashing, second symmetric of hashing, to study our equation, sigma 2. Okay. So, and now let me discuss what is the variational approach to study sigma 2. As I already have mentioned, to study the second order PDE, and for the Yamabe problem, when n bigger than or equal to 3, we have an easy functional, natural functional to study, to boil it down to variational problem, and that's just the integration of RG integration. But when n equal to 2, this functional become a bit less obvious, and that's the functional introduced by Moser. Okay? So that's the Moser functional. And it turns out when n is bigger than 2 and n not equal to 4, when n not equal to 4, if we are going to study this functional sigma 2 to boil it into a constant metric, the functional, variational functional, is just integration of sigma 2. But when n equal to 4, this functional does not work because it's invariant. It's a constant under conformal change. So we are seeking the functional, like the Moser functional for the Gaussian curvature problem to study sigma 2. Okay. What is the variational functional to study sigma 2? It turns out the answer comes out from a surprising resource. So let me tell you what is this. Okay. It turns out that in 2 dimensions, let's review that this second order PDE and then the variational equation, as I already mentioned many times. And independently, people also try to see on high dimension what are the operators. Are there other operators with conformal covariant properties? And turns out in 1983, there is the operator introduced by Panitz. Okay. Panitz, and it's called Panitz operator. And he hand wrote down an operator, which is a fourth order operator when n is the dimension. And the leading order term is the bi-Laplace operator, fourth order operator, double Laplace. And then there is some second order term. The second order term of this operator, the coefficient is related to the geometry. And then plus a zero order term of curvature, there is a coefficient n minus 4 over 2 of a curvature. And he pointed out this operator, this is in his relation to study Maxwell equation, has conformal covariant property. And he did this for n bigger than or equal to 5. Why? Because, for example, when n is not equal to 4, you can see what is the curvature from the operator. the operator operating on phi equal to 1 gets you the curvature. So the relation between the operator and the curvature is obvious. It's like from conformal Laplacian, you see the scalar curvature. So that's why he did it for n not equal to 4. But then it was pointed out by Tom Bronson. He said that although the formula works for n bigger than or equal to 5, one can extend it to n equal to 4. So what does that mean? He looked at the expression of this fourth order operator and just plug in the coefficient n equal to 4, and then there is this operator in dimension 4. And the contribution of Bronson is for this operator, he also introduced a Q curvature. And he wrote down that Q curvature. And that Q curvature is again Qg on n dimension. When n not equal to 4, you plug in n equal to 4 in that coefficient, and you write down this. So there is this, I call it a fourth order curvature, because the curvature is differentiated metric twice, and we differentiate Laplace. So this is the fourth order term, and plus a quadratic curvature. And the contribution of Bronson is to say this is worth study, is satisfy PGW plus 2QG equal to conformal change QGW E4W. Pointed this out. And so this equation on 4 manifold is compared to the Gaussian curvature equation on 2 manifold. He says that means that this Q curvature play a role in PDE similar to Gaussian curvature on 2 surfaces. Okay. So this P operator is easy for R4 Laplace square. On Einstein manifold is also easy. On 4 sphere is Laplace square minus 2 Laplace. And in general, for Einstein metric, that is when Ricci is proportion to the metric, it's just minus Laplace composite with conformal Laplace operator. So not only we have a fourth order operator, we have a Q curvature relating to that. So if one look at this expression of Q curvature, you notice I wrote it in such a term. This second expression here is the sigma 2 we are seeking for, we are looking for. So that means there's a relation between a fourth order curvature Q and sigma 2, which is the Gauss-Bonnet integral. And now, if we look at Q curvature and we think about the comparison to Gaussian curvature, we know there's a natural functional to study Q curvature. And that's correspond, I write it as 2, functional 2, which correspond to Moser's functional. So this is P4WW and then plus 4Q times W, and then a normalization of the volume. After looking at that, we know there's a PDE tool to study Q curvature. How about sigma 2? And then the thing is, we also seek a functional to study Laplace R, functional to study this and try to cancel it out. So the functional to study Laplace R in 4 manifold turns out to be scalar curvature square. Okay. So there's a functional 3 whose Euler-Lagrange equation is Laplace R. So that means to study sigma 2, we first study the functional 2 using PDE tool, and then we study the functional 3, and we cancel it out, and that functional is the functional variational method to study sigma 2. Okay? And that's our approach. So PDE, in terms of PDE, that means to study this, to reduce this fully nonlinear PDE, to study it using variational method, we use this linear functional 2, and then we cancel out 3. And when delta equal to 112, that's just this functional 2. And then we gradually cancel that out. What does that mean? That's the method of homogenization. We have this higher order term, del Laplace square, and then the term we want to study, sigma 2. We first solve a solution for each delta, and we let delta tends to 0. And that's the approach to study this functional. Now let me report a bit about progress on this functional. It turns out in one class of metric, this method is particularly effective, and this direction is the elliptic direction. Okay? So when this Yamabe invariant is positive, and when this remember that's another invariant, when these two numbers all are invariant, conformal invariant quantity are positive, we call it the class A. And the main result is, it turns out metric is in the class A if and only if in the conformal class you can bring scalar curvature and sigma 2 both to be positive. So that means it's in the positive 2 cone. Okay? So this positive 2 cone metric has been well studied by Gaussian and other mathematicians. So it turns out the sign of the curvature already decide modulo the conformal class, the metric in the positive 2 cone. Okay. And that's the result. So we bring in analytic tool to study metric in the positive 2 cone. Okay. And now there's another result I want to report, and that's the result of Gutsky and Street in 2016, a more recent result. It turns out that on 4 manifold, if you start with the metric in this positive sign, these invariants are positive, and if the metric is not conformal to S4, then the GW in G with sigma 2 equal to 1 is unique. Okay, unique. So in the same conformal class, if you seek the representative, so it's canonical, so the metric becomes curvature equal to 1, that's unique. Okay? And this result is surprising and important in the sense that we know that one of the problems of the Yamabe problem is the representative in the same conformal class, the scalar curvature equal to 1 is not unique. And that adds to the difficulty of classification result when you have a canonical representative which is not unique. But if you do it on sigma 2, it's unique. Okay? Unique. And that means that this is a natural quantity to study. Okay, and now let me bring some consequence of this result. And it turns out using this kind of approach, one can classify a slice of the 4 manifold when a manifold 4 manifold is in a neighborhood of the 4th sphere. Okay? So if these two conformal invariant quantity, if integration of Weyl square is less than this integration of sigma 2. So for example, from 4th sphere, the Weyl square is 0. And this integration sigma 2 is the Euler characteristic, is A pi square. So that happens on 4th sphere. But this theorem says this happens, then the manifold is already diffeomorphic to S4 or the real projective space, depending on the orientation. Okay? And then the theorem says when it's equal, the next stage, when it's equal, and if it's not diffeomorphic to 4th sphere, because the metric can perturb, and it still can be diffeomorphic to 4th sphere. But if it's not, then we already know the manifold is complex projective space, CP2, GFS. And so it says the limiting case, you compare these two conformal invariant quantity. When one is bigger than the other, it's for sphere, and when it's equal, this other manifold comes in. Okay. And this first part of the theorem implicitly use receive flow method. Okay. So if you want to, the receive flow method at this moment is almost the unique method to prove some two manifolds are diffeomorphic to each other. So it's an L2 version of a receive flow method. And the second part of the theorem uses something. The theorem exclude out because I have its greater. There is another case, and that's when everything is equal to 0. That's S1 cross S3. Okay, and now this theorem also suggests that what happened on S4, you have almost a uniformization theorem in terms of this conformal invariant, and when it's reached, then it's CP2. And then can one continue the program? So for that, one defines this constant, a conformal invariant constant, the ratio between these two conformal invariants. The previous theorem says if this number is between 1 and 0, then it's S4. And then what happens later? And the first lemma is if it's in my positive cone class, and if beta is between 2 and 1, then it's diffeomorphic to S4 or CP2. We know that it's homomorphic to either S4 or CP2. And on S4, when the Betti number, the Schoff dual power or the anti-Schoff dual power of the Betti number vanishes. And then the second thing is when the Schoff dual power is equal to 1, the anti-Schoff dual power equal to 0. Okay. And when beta equal, again, this program has a limit at beta equal to 2. When beta equal to 2, there is a third metric appear, manifold that's S2 cross S2. And this result, depending, in addition to the Gauss-Bonnet formula, there is the signature formula, Atiyah Singer signature formula, and there's another topological quantity, and that's called the index, the Betti number B2 plus minus P2 minus the torsion. It's equal to Weyl square minus Weyl minus square. So use the signature of the formula, another topological invariant. Okay, so and we now try to bring the homomorphism type down to diffeomorphism. Let me just report one epsilon progress. And we wonder if beta between 2 and 1 would be the metric already be diffeomorphic to CP2, the complex projective space. And it turns out there is a epsilon, there is a gap, and that gap we hope is 1, but at this moment it's a perturbation argument. We only know there's a gap. And if you add a topological assumption, the second Betti number, the Schoff dual power is positive, then it is diffeomorphic. The method, again, is receive flow. Okay. And now let me say that there is an ambitious program, and with very little progress going on now. That is, we know that there is classification up to homomorphism type of 4 manifold, which allow a positive scalar curvature. That's done in the early 1982, 83 by Donaldson and Friedman. They classify all such manifolds, and that include S4 and connection, K connection of S2 cross S2, or connection of CP2 with the conjugate class of copy of CP2 plus minus. One is B2 plus equal to Schoff dual, the other is anti-Schoff dual. When G is in A, one knows there is a constraint of 4 plus 5L. And then among this class, one first want to find out what are the metric which is in a positive 2 cone. That has not been done, but we know that there are many such manifolds in the list. So the program is trying to decide up to diffeomorphism type among this classification up to diffeomorphism type according to the size of this conformal invariant. But that's an ambitious program. Okay, now in the remaining time, let me say a little bit about what happened for 4 manifolds with boundary. Okay. So again, on 2 manifolds with boundary, we have the tool of a Gauss-Bonnet formula. There's a Gaussian curvature plus the boundary curvature. And with this tool, we have the corresponding, remember we use Gaussian curvature is prescribed by Laplace operator on 2 surfaces, and the boundary curvature turns out to be prescribed by the Neumann operator, dd, dw, dn. So the geodesic curvature is prescribed by this dw, dnormal on a conformal factor w plus k equal to kgw EW. So the first attempt to try to generalize things on 4 manifolds with boundary is to find the analog of this Neumann operator on 2 surfaces. And some work has been done by myself and co-author Qingjie. And so what we do is we generalize this Laplace operator and Neumann operator from 2 surfaces to 4 manifold. Laplace is replaced by the Penny's operator we talk about, and then this Neumann operator is prescribed by a 3rd order operator. And the Gaussian curvature on 2 surfaces is described by Q curvature, and the geodesic curvature is prescribed by T curvature. Okay, so let me say 1 word about this. And it turns out this P3 operator is also having conformal covariant property and prescribed Q curvature. Its leading order term is a 3rd order operator. This is Laplace composite with dd normal and plus dd normal composite with the boundary Laplacian. Okay. So this is the operator, and with this operator, one can take another look at a Gauss-Bonnet formula with boundary, and then there is this interior term and the boundary term. Again, the boundary curvature in this case is split into 2 parts. One is a pointwise invariant part, and one is prescribed by the T curvature. So based on this type of analysis and thinking, one can begin to study this Q curvature and plus a boundary term. And the boundary term, so instead of this integration Q, one begin to study integration Q plus the boundary invariant. Okay. And the formula is complicated, but on the other hand, in a simple case, when the manifold is with totally geodesic boundary, that means the second fundamental form is trivial, then the T operator can be written down explicitly. It's dd normal of the scalar curvature. And remember that this Q curvature is just Laplace R plus sigma 2. And in this case, Q plus integration of this term, this boundary integration Q of this Laplace R happen to have this coefficient which cancels out with that T. So on 4 manifolds with boundary, the invariant we are seeking at is sigma 2 again. Okay? So instead of Q curvature, we now somehow on 4 manifold with boundary, the natural conformal invariant term to study is integration sigma 2 again. Okay. So I don't think I have time to cover. How much time do I have?
Like 10 minutes, 12 minutes.
Oh, okay. So I have another about 12 minutes. So let me cover application of relating this invariant to a concept in string theory. Okay, so there is one problem we are interested in, that is, given a manifold, when can you fill it in, treat M as a boundary of another manifold, which is Einstein, which is conformally Einstein, as a boundary of Einstein manifold. Okay, and this problem comes in this ADS-CFT conformal theorem proposed by Bardacina in 1998. There are lots of papers in this direction to study quantum gravity. And it also comes in problem in geometry when one wants to study structure of non-compact asymptotically hyperbolic manifold. Okay. So what does that mean? So on a manifold X with boundary M, first we have a defining function on the manifold. And so that is a distance function, R positive on X, and R equal to 0 on boundary, and dr is not equal to 0 on M. We call it a defining function. So on a manifold with a metric G+, we call the G+ may not be compact, but on the other hand, we call it conformally compact if multiplying a distance function to it makes it compact. Okay. So in this case, we call this boundary metric a conformal infinity of the original manifold. Notice you have many different choices of this defining function. So the boundary metric is only decided up to a conformal class. You can multiply it by another distant positive factor to R and still a defining function. So the boundary is the conformal infinity, it's a conformal class. So the idea is to study this conformal class of metric via its extension. And if Ricci is equal to minus NG+, we call it conformal compact Einstein. And so this means Poincare Einstein. Okay. And we remark that we call this CC manifold. We can always choose. Once you know that this defining function exists, you can always make a special choice so that this compactified metric is totally geodesic. That is, we can make such a choice. So the example is, the typical example is upper half space with Poincare metric. Okay, so on the upper half space, we have the Poincare metric. And this Poincare metric, of course, is not compact. You multiply it by y squared, it's still not compact, but it becomes flat. So in this case, the Rn, Euclidean space, is the conformal infinity of Poincare space, Poincare metric on upper half space. And then one can transfer this to the Euclidean ball, actually the hyperbolic ball with sphere as conformal infinity. So in this case, the hyperbolic metric is one of the distance function squared. And then there is a non-trivial choice of this defining function. Written this, we get this hyperbolic metric is R minus 2 dr squared plus this 1 minus r squared over 4 squared, and the GC is the canonical metric on sphere. So if you multiply r squared to G plus, and you restrict it when r equal to 0, then it's the sphere metric. So that means sphere is the conformal infinity of hyperbolic ball. That's the model case. Okay. And of course, there are much more sophisticated examples of conformal compact Einstein manifold, ADS, Schwarzschild space, and so on. So the problem of given a manifold, when can you conformally fill it in so that it's the conformal infinity of a hyperbolic metric is first studied, means there are lots of study. There is an important work of Pfefferman and Grant in 1985. They call it the NP metric construction. What they say is on the boundary, you can have a neighborhood, perturbation of the neighborhood, such that this Einstein metric exists, okay, construction. And there is also work of Guski and Sakahidi extended. Pfefferman and Grant did it for analytic metric. And there is an extension to arbitrary smooth metric. And so this is an existence on a neighborhood. And there is the only concrete existence result is by Grant and Lee. Etch in a small smooth neighborhood a perturbation of the canonical metric on sphere, perturbation of the standard metric on Sn has a conformal fill-in. Okay. And now there is also a non-existence result. Okay. And in a very recent work by Guski, Han, and Stolz, they construct many examples such that the 4k minus 1 sphere, here k must be greater than or equal to 2. Say, for example, 7 sphere does not allow a B8 filling in. Okay. So if you constrain yourself to B8, say, then S7 cannot be the conformal infinity of B8, okay? When this metric has positive Yamabe constant. Okay? So this construction doesn't exist, actually use Atiyah Singer Pertotti's index theorem. Okay. And so there is also uniqueness result and non-uniqueness result. Uniqueness result says, for sphere, hyperbolic ball is the unique fill-in. And this proof actually depends on positive mass theorem. And then there is the question of what about the metric construct by Grant and Lee? They say on a perturbation of the sphere, you also have conformal filling in. Is that unique? That's still an open question. And only on full manifold, using the method I have described, the special tool, one can show, indeed, Grant and Lee metric perturbation is unique on S3, okay, S3. And on the other hand, there is also non-uniqueness result. That makes the subject interesting, and that's the construction by Hawking and Page. Okay, so given the same conformal infinity, there are different ways of conformal filling in. Okay. Okay. So now let me say the renormalized volume. Okay. So we know that the hyperbolic metric has volume infinite. And then there's this concept of what is, say, think about on hyperbolic metric. If you push it in, you look at away from the boundary, r greater than epsilon. Then, of course, the volume is finite, but it depends on epsilon. The leading order term is epsilon to the minus n. And now one take the expansion in terms of epsilon, and then there is the log epsilon term, and then the next order term. And the subject we are interested to study is what is this V, and which is called the renormalized volume, a concept introduced by Wheaton and so on. Okay, we are interested to study this V plus V, okay? And that's called renormalized volume. it turns out I'm talking about uneven. L is independent of H, or conformal class, okay? But V is not, okay? L is. And the work of Grant and Zosky, Pfeffman, and Grant says L is actually integration of the Q curvature on the boundary. Okay? So that's the invariant we talk about. But when n is odd, dimension is n is odd, say 3 plus 1, 3-dimensional boundary. Okay, so in that case, the log term disappears. We have the renormalized term. And the result we have is this renormalized term is actually the sigma 2, the invariant we talk about on 4 manifold. You extend it in, okay? So that's the renormalized volume. So I run out of my time, and let me just say one word that the proof of it is analytic work and based on a special choice of metric, and that's first done by Grant and Lee, talk about this special equation, and then choose the metric G star equal to special equation, which has Q equal to 0 and T equal to a constant. And based on that, one can begin to show this renormalized volume is this Q curvature is equal to 0, and that T curvature is just a PD normal RG, and one can see using PDE, that's the renormalized volume. Okay? So this invariant, in this case, is the renormalized volume in 4 manifold. So I think I will not touch on the, an open question is, for the entire class of S3 with a positive metric scalar curvature on the boundary, does that allow conformal filling in? We know on S7 it doesn't, but the S3, the positive Yamabe class metric, has only one path-connected component. So that makes it possible. The problem may have a positive answer, but it's still an open question. And that's a direction me and I and some of my co-workers are working on. So I thank you your attention for listening to my talk.
So we have time for maybe 1 or 2 questions or comments.
Okay. Very beautiful talk. I had a question. There was a 2 dimensions. There was a determinant formula.
Yes.
Is there an analog of this?
Yes. Yes, there's analog of that formula, and that's by Bronson and other people, restrict to conformal class. There is a formula. I can explain to you later. Yes, there is a restrict to conformal class, there is a formula. That's actually the first time the Q curvature comes in. Yes, want to begin to talk a log determinant of conformal Laplace, the quotient of that has 3 types of term, and one of them is Q curvature. Sure, yeah. That's actually the motivation to look at the Q curvature to start with, because it compared to the Polyakov formula, it comes naturally. Yes, yeah. Okay.
Okay, so there's a question there.
I have a quick question. So you mentioned when K was equal to 2, you pointed out lambda of I and lambda of J. What is lambda, like, the distance for in that scenario?
Okay. Lambda of J. Lambda is the eigenvalue of, we treat A as an n cross n matrix. Although it's a differential form, think about it, a matrix. So it has eigenvalues. These lambda are eigenvalues. Lambda I, lambda J, eigenvalue of this matrix. Yes, yeah.
So I think maybe we can adjourn here. We are going to go back to schedule, so we'll resume at 11:30. This coffee break outside, and thank you again, Alice.
Sure.